Welcome to today's paper reading. Today's paper is titled RAFT, Adapting Language Model to Domain-Specific RAG. This paper, titled RAFT, Adapting Language Model to Domain-Specific RAG, is authored by Tianjun Zhang and colleagues from the Department of Computer Science at UC Berkeley. The paper is currently under review. The paper discusses the standard practice of pretraining large language models, LLMs, on extensive textual data corpora, which is now a common approach for many downstream applications. When integrating new information into these pre-trained models, methods such as RAG-based prompting and fine-tuning are typically employed, but the optimal approach remains uncertain. This paper introduces Retrieval Augmented FineTuning, RAFT, a novel training technique that enhances the model's capability to answer questions in open book in domain settings. RAFT trains the model to disregard irrelevant documents, termed distractor documents, and cites the correct sequence from the relevant document to answer the question. This, combined with RAFT's chain-of-thought style response, improves the model's reasoning abilities. RAFT consistently enhances model performance across datasets like PubMed, HotPotQA, and Gorilla, offering a post-training recipe to improve pre-trained LLMs for in-domain RAG. The paper addresses the adaptation of large language models, LLMs, to specialized domains, where general knowledge reasoning is less critical compared to maximizing accuracy based on specific documents. This adaptation is essential for emerging applications in various fields. The paper explores two main methods for adaptation: in-context learning through retrieval augmented generation, RAG, and supervised fine-tuning. Additionally, it proposes a novel strategy called Retrieval Augmented FineTuning, RAFT, which aims to combine the benefits of both methods. RAFT focuses on fine-tuning models to incorporate domain-specific knowledge while improving performance in retrieval augmented generation tasks and ensuring robustness against distracting information. Figure 1 illustrates different strategies for preparing for an exam. A. Fine-tuning methods either memorize input documents or answer practice questions without referencing them. B. In-context retrieval methods fail to utilize the learning opportunity provided by the fixed domain, akin to taking an open-book exam without studying. In contrast, C. RAFT combines fine-tuning with question-answer pairs while referencing documents in a simulated imperfect retrieval setting, effectively preparing for the open-book exam scenario. In the context of closed-book exams, LLMs do not have access to any additional documents or references. This scenario is analogous to a chatbot that relies solely on the knowledge integrated during pre-training and fine-tuning. Conversely, open-book exams allow LLMs to refer to external sources of information, such as websites or book chapters. Here, the LLM is typically paired with a retriever that fetches relevant documents, influencing the LLM's access to domain-specific information. The paper specifically focuses on domain-specific open-book exams, where the LLM is fine-tuned for a particular domain, such as enterprise documents or code repositories. This setting requires adapting the LLM to be robust to varying numbers of retrieved documents and potential distractors. Figure 2 provides an overview of our RAFT method, highlighting how it adapts large language models, LLMs, to read solutions from a set of positive and distractor documents. This contrasts with the standard RAG setup, where models are trained based on retriever outputs, which involves a mix of memorization and reading. At test time, all methods adhere to the standard RAG setting, where the model is provided with the top K retrieved documents in the context. In this section, we introduce RAFT, a novel approach to fine-tuning language models for domain-specific open-book exams. We start by discussing supervised fine-tuning, SFT, where the model is trained on a dataset of question-answer pairs to improve its ability to answer questions. This training can also be used in a retrieval augmented generation, RAG, setting, where additional documents are introduced to help the model answer questions. RAFT introduces a modified training data preparation method, where each data point includes a question, a set of documents, and a chain-of-thought style answer. The training data is prepared such that for a fraction P of the questions, the golden document is included along with distractor documents, while for the remaining fraction, 1P, only distractor documents are included. This approach forces the model to memorize answers in some instances, enhancing its performance in domain-specific RAG settings. A key enhancement in RAFT is the generation of a reasoning process, such as chain of thought, which includes source citations and detailed explanations, boosting the model's accuracy in answering questions. In evaluating the RAFT model, we observe that it consistently outperforms the baseline models, including Llama 2-7b. Specifically, RAFT demonstrates significant gains on datasets like HotPotQA, with improvements in robustness when combined with RAG. The inclusion of chain of thought (COT) in the training process significantly enhances the model's robustness, preventing overfitting to simple answers and improving overall accuracy. A qualitative analysis highlights RAFT's ability to accurately answer complex questions, such as identifying a screenwriter, while a domain-specific fine-tuned DSF model fails to extract the correct information from the context. This underscores the importance of incorporating both standard instructional tuning and context comprehension in model training. Table 1 illustrates how RAFT enhances retrieval augmented generation (RAG) performance across specialized domains including PubMed, Hotpot, Hugging Face, Torch Hub, and TensorFlow Hub. The table shows that domain-specific fine-tuning significantly boosts the base model's performance, with RAFT consistently surpassing existing domain-specific fine-tuning methods, whether or not RAG is applied. This indicates the importance of training the model with contextual information. The table also compares RAFT's performance with Llama fine-tuning recipes and provides GPT 3.5 as a reference. Notably, RAFT demonstrates substantial improvements, particularly on the Hotpot and Hugging Face datasets. Table 2 presents an ablation study on the chain of thought (COT) approach, showing the performance of RAFT with and without COT. The results indicate that incorporating COT significantly enhances the fine-tuned model's performance across various datasets. Notably, there is a 9.66% improvement on the HotPotQA dataset and a 14.93% improvement on the Hugging Face dataset. This suggests that COT not only guides the model to the correct answer but also enriches its understanding, thereby improving overall accuracy and preventing overfitting. Figure 4 illustrates the performance comparison between the RAFT and DSF models on the HotPotQA dataset. The DSF model incorrectly extracts a film name instead of the correct screenwriter's identity when asked a specific question. In contrast, the RAFT model accurately identifies the screenwriter, demonstrating its superior ability to derive relevant context from provided documents. This comparison highlights the importance of incorporating both standard instructional tuning and context comprehension in model training to enhance text processing capabilities. Figure 5 investigates the hyperparameter p%, which represents the percentage of training data including golden documents. Results from NQ, TQA, and HotPotQA datasets suggest that an optimal p% varies, indicating that including a mix of data without golden documents can enhance in-domain RAG performance. In this section, the authors investigate how the inclusion of distractor documents affects the performance of RAFT when augmented with top-K RAG results. They found that training solely with golden documents can reduce the model's ability to disregard irrelevant information. To address this, RAFT integrates golden documents with a mix of irrelevant ones, prompting the study of the ideal fraction of distractor documents during training. The authors also examine the impact of varying numbers of test-time documents on model performance, finding that training with distractor documents makes the model more resilient to fluctuations in test-time document numbers. This robustness is further validated by the consistent performance of RAFT across different test domains, such as natural questions, NQ, Trivia QA, TQA, and HotPotQA, HOPA, when trained with a setup of 1 golden document and 4 distractor documents. Figure 6 investigates the robustness of RAFT to varying numbers of test-time documents across 3 domains, NQ, Trivia QA, and HotPotQA. The study reveals that the optimal number of training documents differs by domain, with NQ requiring 4 documents, Trivia QA 3, and HotPotQA 2. Notably, training exclusively with golden documents results in suboptimal performance. This suggests that incorporating a mix of relevant and irrelevant documents during training enhances the model's ability to perform well under varying test conditions, highlighting the robustness of RAFT. In this section, we discuss three main areas of related work. First, Retrieval Augmented Language Models, RAMs, enhance large language models by integrating a retrieval module. This significantly improves performance in various NLP tasks such as language modeling and open domain question answering. Examples include Atlas, which fine-tunes T5 models with a retriever, and Retro, which modifies the decoder-only architecture to include retrieved texts. Second, the issue of memorization in large neural language models is explored. Researchers have developed methodologies to quantify the extent of memorization, which raises significant privacy concerns. Finally, recent works focus on fine-tuning pre-trained large language models for retrieval augmented generation (RAG) tasks. These studies construct specialized datasets for fine-tuning and test the models on the same set of documents, which is a slightly different scenario from our approach. The RAFT training strategy is designed to improve the model's ability to answer questions in open-book settings within a specific domain. Key design elements include training with distractor documents, structuring the dataset to include contexts without golden documents, and formulating answers in a chain-of-thought manner with direct quotations from relevant text. Evaluations conducted on PubMed, HotPotQA, and Gorilla API Bench demonstrate RAFT's significant potential for enhancing performance. These crucial design decisions highlight the strategy's effectiveness in various domains. Thank you for watching.